So good morning, everybody. We are the authors of the paper that was kindly invited for this journal first at ICSME. So the idea is actually that we are going to explain a little bit in this teaser what was the idea behind this paper. So it actually is the classic case where two groups came together, and there was like Nemitari and I, and then we found that somebody else was doing something similar somewhere else in the world. So we said, should we collaborate together? And actually, so it started for our group from when we realized that there was like a lot of empirical research that was doing so they were accumulating lots of data, but it was clear, at least it was clear for us, that the data that they were sort of accumulating was not very well clustered around the application domains or the topics that the software systems were belonging to. So I called Davide, and then he told me that essentially, so there was like an importance of the clustering. So Davide, maybe he can speak about the importance of clustering of domains and application systems.
Yeah, thanks, Andrea. Essentially, when you approached us, we were working on the CrossMiner project, where we were essentially identifying or understanding the similarities between different open source projects, right? So when you want to assess if two projects are similar, because you want to rely on this information for providing some recommendations. And at that time, we were using clustering techniques for doing that. Essentially, you know that the clustering is among one of the fundamental techniques in knowledge mining and information retrieval for understanding how different objects can be distributed in different groups, right? And in our work, in the work that we have done in the journal paper that we are presenting, essentially we by using these clustering techniques, we want to assess to the degree to which two different programs are similar, and also to what degree they are similar. So essentially, we define the different similar techniques for doing that. So, of course, all these details about the clustering techniques that we use are in the paper, but this is the main message and the main things that we are discussing in the paper.
So then, the first clustering techniques that we used was the CrossSim one. But actually, probably Yuri can tell us about the different techniques that we used.
So in our paper, we use three different techniques. So the first one is like David and Andrea said, is CrossSim. The second one is the clustering based on manually classification. And the third one is the LDA-informed clustering. So the first one is the technique that we developed in the context of CrossSim project, where we are representing open source project like a graph, and then we are comparing similarity between two projects by using graph-based similarity. For this reason, we represent a project as a graph by using different kind of nodes and edges. In particular, a node will be a project, or an API that uses the project, or a developer that develops a specific classes of the project. And the edges is the relation that occurs between two nodes. For instance, a developer can develop a specific class that is contained by a specific project, and then we use this graph representation in order to assess the similarity between two projects. Then we use a manual classification that classifies 200 repository in 6 categories. This kind of clusterization is based on a project description, and it is provided done by a manual classification. Then we use the information contained in the class of a project in order to define another classification that is LDA LDA-informed cluster. So we extracted from the classes the identifier, like the name of the class, the name of the variable, and so on, and then we represent this in a document in order to use LDA-informed cluster and then classify the project. And then I think that Fong is going to talk about the result for CrossSim clustering.
Yeah, sure. So as Julie mentioned, we use CrossSim as because we exploit a graph-based representation to represent all the research on the projects in the graph, and we use also dependency, also the people who start or commit to a project, and we use structure of the graph to compute similarity. So when we use CrossSim for computing the similarity among projects, and then we use the result for doing the clustering. So we can see that all the statistical tests for the 6 pairs of the considered projects there, and we can see that we cannot reject all the null hypothesis, because the p-values for those experiments are like, let's say, not lower than 0.05, because the reason for that, because you know that CrossSim computes similarity based on the structure of the project dependency, and also based on the stargazers, the committers. So even when the projects, they share many dependency in common, but still they are committed by different people, and they are star by different people. So that is the reason why the similarity can be lower, and that is the result is we cannot conclude that the cluster are structurally different from each other due to the similarity computed by CrossSim. So I think Dimitri is going to explain a little bit more about the result, the other techniques. Yes.
Okay. Yeah. So I think in the first technique was based on the CrossSim, and moving on to the second technique. So the second technique was based on the description of the project. So the descriptions of the project from the README files or the documentation was used to cluster these projects into 6 categories, namely application software, documentation, non-web libraries, frameworks, software tools, system software, and then finally web libraries and frameworks. And this data set was from a previous publication and by Borges and Valente. And then we took the Java subset of projects out of a sample of 5,000 projects. So we took 520 Java projects, and based on the Kolmogorov-Smirnov null hypothesis test, we could strongly reject the null hypothesis. And this was because the object-oriented software attributes amongst the different software clusters were sort of showing differences. And in terms of the third technique, we took the 100 most popular GitHub projects based on the stars that they've received from the community. So we took the top 100 most starred projects from GitHub, again, with Java as the main language. And then we also did the null hypothesis testing again, using the object-oriented metrics. And similarly, for the second sample, with the third sample, we could also reject the null hypothesis and fail to reject the alternative hypothesis. And interestingly, these results show that software projects could show different characteristics based on their domains or categories. And the projects are also sensitive to the clustering techniques as well. So you observe differences based on the clustering techniques applied. And when you also add more categories as well, in most cases you also observe quite clearer differences also. And I think we also did a correlation test just to make sure that we didn't reject the null hypothesis by mistake. So within each category, we did the correlation test between pairs of these object-oriented software metrics. And interestingly, we also found that the correlation was also sensitive to the domains or the software categories as well. So I think Andrea would conclude.
So I think we are opening the debate in terms of when you actually cluster software systems in categories, you will create strongly different results. So and I think that was more than I was expecting from this particular paper. So I hope that we teased you enough to join you at the presentation itself, and then I'll hopefully see you there. And thanks a lot.
Thank you.
Thank you.